Pease from the University of Dundee. Alison got her start studying mathematics and philosophy at the University of Aberdein. She then went out into the real world and worked as a high school teacher, qualified as a high school teacher, worked as a high school teacher, then saw the light and came back to Edinburgh Computer Science Department, now Edinburgh Informatics, and did a PhD in computer science and AI with Alan Smale and Alan Bundy. She now works at the University of Dundee, and she's taken forward some of these aspects of broadening out how we think about the formalization of mathematics by looking at explanation in mathematical practice.
Thank you. So this work has been done in collaboration with all the folk on the slide here. Ursula's here, as you know, and Joe is just there as well, if you want to chat to any of us about it afterwards. So our main research agenda, which just seems to get bigger the longer we spend doing it, is how do people do mathematics? And the reason that we think this question's interesting is in order to try and bridge the gap between automated theorem proving, automated theory formation, interactive theorem proving and so on, and mathematicians. So the idea eventually would be to develop and implement systems which are able to do mathematics in a more human-like way, whatever that means. So this research program is about investigating what that means, what human-like mathematics is. So there's lots of questions that we're looking at, and we have been now for a few years, and I hope we'll continue. Ursula mentioned a few of them in her talk on Wednesday. So what do they talk about? And we saw a breakdown of different things that they discuss in conversations. What do they value? How do they explain things? And what are the patterns of communication? So we're really looking at informal mathematics and trying to extract patterns of communication there. So the question that I'm going to focus on today is how do they explain things? If we get time, I'll talk a little bit about patterns of communication as well. But we're quite guided by a quote by Tim Gowers here. If we wish to teach computers to find proofs, it is likely to be a good idea to reflect on how we do so ourselves. So that's pretty much our guiding methodology, I suppose, in a nutshell there. So focusing in on explanation, we organised a workshop in Edinburgh back in 2012. And Michael Atiyah made a very nice comment. I published a theorem in topology. I didn't know why the proof worked. I didn't understand why the theorem was true. This worried me. Years later, we generalized it. We looked at not just finite groups, but Lie groups. By the time we'd built up a framework, the theorem was obvious. The original theorem was a special case of this. We got a beautiful theorem in proof. So he was really worried. Although they had proved something and they were happy with the proof wasn't satisfactory in a way, mainly because they didn't understand it. It wasn't an explanatory proof. So he really highlighted the importance of explanatory proofs in this comment. Other mathematicians, there's a quote by Bourbaki, indeed every mathematician knows that a proof has not been understood if one has done nothing more than verify step by step the correctness of the deductions of which it is composed, and so on. So we looked around at a lot of different disciplines and what they have to say about explanation in mathematics. So this is a little bit by the mathematicians themselves. Philosophers have a lot to say about explanation in science. They have a little bit less to say about explanation in mathematics. There's this one idea that there's no such thing as explanation in mathematics, and the idea behind this is that explanation is related to causality, and causality doesn't make sense in mathematics, and therefore there's no such thing as explanation in mathematics. Van Frassen developed a theory whereby all explanations are answers to why questions. So these might be implicit why questions, but there will be associated a why question with demand for an explanation. And Kitcher thought that explanatory proofs must unify, so they occur primarily as an appeal to a higher level of generality. So what about automated theorem proving researchers? Alan Bundy commented, the detailed logical proofs typically produced by automated provers can have an order of magnitude more steps than a typical textbook or journal paper proof. This extra detail can be tedious to wade through, mathematicians find informal proofs more accessible and understandable. So again, highlighting the idea that a proof should be explanatory. And another quote here in this lovely paper by Danilo Lipton and Perlis, along similar lines. And finally, we looked at AI and the thinking in AI about explanation. This goes back quite a long way to early expert systems, where the idea was that if they output the process or the reasons behind a decision that they've made, then it might be more believable or more understandable or more felt to be more trustworthy or so on. So very early on in the history of AI, people were considering having their intelligent systems output an explanation alongside its output, whether that's a decision, a classification, or whatever that is. Douglas Walton, who's principally a philosopher, he retrieved some nice work from this period on expert systems, on different types of explanations that can be given. So trace explanations reveal the trace of reasoning. That's the object level reasoning that has taken place. And strategic explanations reveal the problem-solving strategy. So that's more at the meta level. And then deep explanations take into consideration the person who is being explained to and the perception of their knowledge base. So what is it that they might not understand, and can we explain that? So can we explain it at the right level for them and the right sort of thing? So he retrieved this very nice distinction. There was there's a field called explanation-aware computing, and they held a series of workshops called Exact. As far as I'm aware, I think they've finished now, these series of workshops. But I did attend one of them, and they were concerned with enabling smart devices to explain their reasoning. So if you've got a kettle that's just turned itself on, it tells you why it's just, I thought you might want a cup of tea, it's 11 o'clock, you normally have a cup of tea at 11 o'clock, so I'll just turn myself on, that kind of thing, rather than just seemingly randomly going on and off and not explaining what it's doing. So there's some work done there. And much more recently, DARPA have started this idea of explainable AI, or XAI. This is I've just taken the slide from one of their websites on what it is. So this is principally for machine learning. Okay, so the explanation is not necessarily how the system arrived at something, but it's trying to elaborate it a little bit. So the idea is that AI is getting increasingly sophisticated, and we need to bring the users along with us, as it were, to be able to question the machine. Why did you do something? Why didn't you do something else? When did it work? When did it fail? And so on. So this is quite a recent initiative that's just started. What we wanted to look at is what actually happens. What is explanation in mathematics, and how we've now looked at how different people talk about it. But how about investigating it for ourselves? So our approach featured these ideas here. We very much wanted it to be based on empirical data. So it had to be grounded in work that mathematicians have done, not so much mathematicians talking about what they do, but actually what do they do. We wanted it to describe everyday mathematics. So one criticism of some theories, quite often theories in philosophy, is that they cherry pick domain-changing examples, the big names, the big results, and then they generalise from that to all mathematics. Of course, everyday mathematics is much more common than that sort of maths, so we wanted to really focus on that. We also wanted to look at collaborative mathematics, and this is something that a lot of the accounts omitted. They saw it as kind of a solitary affair. Of course, mathematics is not a solitary affair, so we really wanted to incorporate the social side of mathematics. And we wanted to look at the backstage. So this is from a metaphor originally from the sociologist Goffman, and then taken up by Hirsch and applied to mathematics, where institutions have both a public face and a private side. So the public face of mathematics would be the university, the textbooks, the public seminars like this one, public lectures and so on, and the backstage, or the private bit, will be the scribblings on whiteboards, the informal conversations over coffee, the bits that didn't work out and never made it into the paper, all that sort of thing. So we wanted to focus on what goes on in the backstage. And again, this is a contrast to certainly what a lot of the philosophers had focused on. And they tended to look at the final polished papers and look at explanation in those. So the hypotheses from the different disciplines that we'd looked at, we developed some hypotheses that there is such a thing as explanation in mathematics. We formulated it like that. We wanted to find support really for our hypotheses. We tried to find things that we thought might work. All explanations are answers to why questions from Van Frassen. The explanation occurs primarily as an appeal to a higher level of generality, and explanations can be categorized as either trace explanation, strategic, or deep explanation. So this largely comes from the literature. But we also thought about implicit assumptions that people made when they talked about explanations in mathematics, and across all of the different disciplines that I've just mentioned. There was no talk of the explainer and the personality of the personal thing who was doing the explainer. So the assumption, I think, is that explanations can be considered independently of the explainer. There was a very big assumption across the board that explanations in mathematics are about proof. It's about whether a proof explains the theorem or not. So proofs can be explanatory or not explanatory, but if we're focusing on explanation, then we need to look at proofs. And that was an assumption that was made by most people, I think. And the explanations happen or fail to happen, I guess associated with the above point, that they happen at the end of the process of proof discovery. So we wanted to question all of those, because none of those seemed very obvious to us. So we incorporated 3 more hypotheses to test. That explanations in mathematics contain purposive elements, so we can talk about beliefs and desires and so on of the person explaining. Explanations can occur in different mathematical contexts, not just proof. And explanations in mathematics are a social phenomenon. So Ursula mentioned our source material, so I won't go through that in too much detail, but we've been looking at online fora as sources of some things that mathematicians do. So in particular, the polymath blogs here by Tim Gowers, or started by Tim Gowers. So Nielsen wrote that these were potentially revolutionary, the leading edge of the greatest change in the creative process since the invention of writing. At least 3 of the 11 experiments have led to published research. So they are successful to a certain extent, possibly not yet proven to the extent that Nielsen thought. They had rules of engagement, which Ursula mentioned, and they provide us, or people like us, ethnographers of mathematics essentially, with a substantial corpus on mathematical practice, so it's really useful for us. And Gowers said that it may be the first fully documented account of how a serious research problem is solved, complete with false starts, dead ends, etc. It may be that the open nature of the collaboration was in the end more important than its size. He said that in 2009 after the first polymath discussion. Okay, so the International Math Olympiad is an annual competition. There's about 500 high school students a year take part. Nearly 17,000 people have competed since its inception. And many of those who take part go on to have mathematical careers, and some at a very outstanding level. 14 of the 36 Fields medalists were IMO participants. Mini polymath is a sort of a blend of the big polymath and the International Math Olympiad. So the idea is that one of the problems at the Math Olympiad is posted each year on a blog for people to solve collaboratively. And again, an open invitation to anybody to participate, and following the same sort of ground rules as for the large polymaths, where people, well, it's not competitive, it's collaborative. People are asked to put in a quantum of progress each time, so kind of brainstorming rather than necessarily going off, solving the problem and coming back and just putting that up. And to be polite and all the other things. So there have been 4 of those conversations take place, and these 4 comprise our data for looking at explanation in mathematics. So I'll just briefly put up the 4 problems. This was the first one in 2009. So this was question 6 from the Math Olympiad, and there were 356 comments there, and between 81 and 100 participants, depending on how many of the anonymouses were the same person. From 2010, that's the problem there. I think I'll have to put them up quite quickly, but I just wanted to show you what the sort of thing they are. And we had 128 comments there, a lot fewer participants. From 2011, what was the problem there? And the final one in 2012. Okay, sorry to be quick with those. Okay, so our total data set comprised all of those 4 conversations, 742 comments altogether, with around 200 participants. And it was spread out over time in this way. Typically, they gain a lot of momentum and tend to go quite quickly and then completely trail off when it's more or less solved or people have gone home.
Sorry, can you explain the colours on that?
Oh, that's just for the year. Sorry. So the 2009 is blue. I don't know if you can see these little. There's a little key there. You probably can't. That's 2009. Blue's 2009. This one's 2010. 2011's grey, and 2012 is the light yellow. Okay, so is this data representative of mathematical practice? Well, we get this question quite a lot, and we answer it by asking another question back. What is mathematical practice? Don't know. And we argue, well, there is no single mathematical practice. There are lots of different cultures of mathematical practices. Matthew Inglis down in Loughborough challenges what he calls the assumption of homogeneity. And he's conducted empirical studies into whether there's agreement between mathematicians. And this is even mathematicians who you might think would be in the same culture. So even the same area of mathematics, or research mathematicians at universities and so on. And found actually that there's a lot of disagreement between them on whether a proof is valid, whether a proof is beautiful, and so on. So there's not even necessarily, even within the cultures that you think are sort of the same, people disagree on things. And there's clearly lots of different kinds of cultures, and there have been various conference series on mathematical cultures and practices along those lines, and different disciplines looking at different things. So you have ethnographers sometimes looking at patterns in the sand or weaving patterns and so on. This is obviously a valid mathematical culture. So we argue that the International Math Olympiad is a mathematical practice, especially given how many people start off by doing that and then end up as professional research mathematicians. But there are some characteristics of the data set which we should bear in mind when we're looking at our conclusions. So here the MPM is the mini polymath. There's a trust issue. This is not an open research problem that the participants are being given. This is something that they believe to be correct, so they think they just need to find a proof. It's a bit educational in a way, the setting, which of course is different from when you're working on an open research problem and then you're at liberty to change it if you think it's not right. The variety of mathematical collaborators is a feature of this sort of collaboration. It tends to have a larger number, I think, than often is the case. And they have a great range of mathematical experience. Some of the participants there were mathematical lecturers and professors, and others were high school students and other things in between. So there's a very broad range of experience and knowledge between all of the collaborators. And of course the medium, the way in which they are communicating is very unique. They only communicate via typed comments in a very structured space, so they have to reply to something in the comments section of the blog. They can't just decide to write a bit of blackboard over there when they're doing something over here. There's no diagrams or scribbles, no gestures, intonation, so a lot of the normal sort of communication is lost. So we do bear those in mind when we formulate our conclusions. Okay, so assumptions that we made in looking at explanation is that there's a structural similarity between arguments and explanations. So techniques which are used to identify arguments, we can use those to identify explanations. So that's important. The second thing is that the subjective and contextual nature of the cues by which people indicate their elocutionary aim means that we can't automate this. We have to manually look at it, and we have to look at what happens around something that might be an explanation. We have to look at something before and something after and try to get all of the cues that we can in order to determine, is this an explanation or is it something else? Maybe a justification, for example. And we also assumed that the same piece of text could be more than one thing. It could be an explanation as well as something else. Crucially here, it could be a proof or a justification at the same time. So we didn't force ourselves to say, is this explanation or only explanation or even primarily explanation? We just said, is this concerned with explanation in some way? Okay, so what did we do? Well, we had two approaches. The indicator approach was our main one because that was exhaustive. And this was based on the assumption, as we said before, that explanations have the same structure as arguments. So indicator words for arguments, which are quite well accepted, or at least their presence is accepted, such as since, because, this is a comma as, thus, therefore, and comma so, that we can use those to look for explanations. And we also added, of course, expla and understand. It would have been silly not to. So we did a complete indicator search for all of those terms across the whole 4 conversations. And then for each instance of an indicator that we found, we looked at what happened, well, what was going on within the sentence, within the comment, before it and after it, in order to determine whether explanation had played a role here. And then we performed close content analysis according to our dimensions, which I'll talk about a bit more detail in a minute. They're connected back to our hypotheses. Our second approach was a random comment approach. So clearly, not all explanations are going to have these indicators in them. So people might explain something with an example, or they might use a semicolon and go into an explanation, or a hyphen, or any odd thing. So we wanted to look to see what other kinds of explanations arose which weren't indicated by those words. So for this wasn't exhaustive because we wanted our approach to scale. Although we could have probably done it for the whole of this data set, we would like it to scale to a much larger data set. So that's our plan, is to look at larger data sets. So we analysed a random 10% of the corpora of comments, and the analysis followed a very similar stages to the explanation indicator approach. We selected a comment at random and we discounted it if it contained an explanation indicator. Then stage 2 was the same. We did the close content analysis. Is this an explanation? And stage 3 was the same. We did the close content analysis for our dimensions of explanation. So elaborating stage 3 a little bit, we identified the explanans, the explanation that is, and the explanandum, which is the phenomenon to be explained. Once we decided this is to do with explanation, we identified those things. We considered whether there is a corresponding why question. These were almost always implicit. We found 5 why questions in the whole data set, so clearly the explicit one was discounted, but possibly implicit. We considered whether there was a level of difference between explanandum and the explanans. So, for example, if the explanation was more general than the explanandum, which might be seen then as a unifying feature. We asked whether the keyword occurred in the context of object level, meta level, or deep, relating back to Walton's distinctions. And we considered what the context of the proof was, what sort of thing was being explained, what sort of explanation was offered for our 3 hypotheses that we'd put forward ourselves. We did a pilot analysis of a subset of our data just to clarify what we meant by our 3 hypotheses. That's 5, 6, and 7. So what do we mean by these individual mathematical and social contexts? And we found that explanations could be related to abilities, knowledge, understanding, and value or goals. So we've got the keywords that we found here afterwards and examples of the sorts of things that we categorised under each of those four. So once we'd found those four via our pilot study, we were able to go through and categorise everything methodically in that way. For the social context, we found different types of mathematical objects. So the initial problem, which is the problem that was given, the Math Olympiad problem, the proof or approach, assertions, specific cases or instances, for examples here, arguments, representations, so ways in which things were represented, which sometimes were changed during the conversation, and properties that something was claimed to have. And the social context, we looked, as I said, we looked a little bit at what was going on before and what was going on afterwards and what the other participants were saying surrounding this example of explanation. And we found that it actually fit really well with Doug Walton's dialogue types here. So he's identified, well, in different pieces of work, he identifies different numbers, but for the ones that we looked at concern these ones. So persuasion is where initially you have a conflict between participants and their goal is to persuade the other one of something that they believe. Inquiry, which it looks like a lot of what we were doing might fit into that, because this is scientific or mathematical inquiry. So the initial situation is that we want to find a proof, and the goal is to find and verify evidence. Negotiation is where there's a conflict of interests and you're trying to kind of get what you want, but find a reasonable settlement that both parties or all parties are happy with. Information seeking is where one participant needs information and asks in general for it, and we did split that off into pedagogical information specifically as well. Deliberation starts with a dilemma or a practical choice. This is more about practical action, so deciding on which action should be taken. And heuristic is essentially, it's a quarrel, so it uncovers a deep conflict, and usually symptomatic of that. Okay, so once we'd done our pilot study, we went through, as I said, and categorised them. Here's an example of the first indicator word. So this was flagged up because understand was an indicator word for us. So I'll just let you read the whole of that little sequence. So Gal here is querying something, asking for an for an explanation. Garth responds, and then Gal says, "Thanks, now I understand." Okay, so in terms of our hypotheses, I put here, well, this is a hypothesis. Firstly, is it an explanation? If it's not an explanation, we just carry on. And then I've got here all the possible answers that we could give, and the one in bold is the answer that we did give. So here, yes, this is an explanation, or is concerned with explanation. What's the explanandum? Why is it important that the points are equally divided? And what's the explanans here? If the line has an orientation, then with half a turn, every point is on the other side of that line. The second hypothesis, is there an implicit or explicit why question? And again, we could just say yes or no to that, and the answer to this was yes, and we've got the why question back there. Is there a distinction of level between the explanans and the explanandum? We answered no to that. What's the wider context? So this is one of trace, strategic or deep, and this did seem to be taking into account Gal's knowledge and understanding. So it looked like Garth was really trying to answer at the right level, thinking about what it was that he might not understand. So we categorised that as deep. What are the purposive elements? Firstly for the explanans and secondly for the explanandum. And here we put as many apply-offs, so we didn't necessarily restrict ourselves to just one. And here we answered understanding. The keywords understand, so that wasn't too hard for both of them. The mathematical context, well, it concerned the proof. This was very late on in their search for the proof. They'd got it essentially, and they were just fleshing out a few details for themselves it also concerned an example because he starts with an example and tries to understand it by using that. And the social context is that he's information seeking. And we also asked whether the explanandum and explanans are given by the same person, and here they're not. So, very social context. So this is just a diagram of our two approaches, the explanation indicator approach on the left and the random comment approach on the right. So the left, the things to note, this was comprehensive. We did it for all of them, whereas on the right we only did it for 10%. And does it contain a keyword? Yeah, it has to be yes to carry on, whereas this has to be no to carry on. But apart from that, they're the same. Okay, so what did we find? In the explanation indicator approach, we found 243 indicators altogether, of which we categorized 72% as actually genuinely relating to explanation. And some of our indicators were more useful than others for that, as you might expect. In the random comment approach, we considered 74, that was 10%, and discarded ones that had indicators in them, so that left 61, and of those categorized 21% as relating to explanation. So the numbers are much lower with this, so the conclusions could also be read with that in mind. So the explanation indicator approach, on average 33% of comments contained one indicator, of which we classified 72. This gives 23% of the whole conversation as relating to explanation, and when we add in the other bit as well, it gives us a combined total of 37% of the whole conversation, or the whole 4 conversations concerning explanation. So that was interesting. Explanation forms a very important part of the mathematical conversation here. For our hypotheses 2, 3, and 4, we got the following results. So in terms of answers to why questions, if you look at the percentages here, this is is this an answer to a why question? Then in almost every case that was true. So there's a lot of support then there for Van Frassen's theory that explanations concern why questions. A lot of support. There's not much support for this. Well, we've refuted it essentially in our data set at least. Is it primarily an appeal to a higher level? And only in 2% we said yes, and or 23% of the random comment approach. So this was the point at which the two approaches gave the most divergent results. So that's something to think about as well. But for the most part, it wasn't an appeal to a higher level. And this distinction turned out to be very neat. It captured most of them here. There was only 1% of the explanation indicator that didn't fit into those, and 0 of the others. So most of them were trace explanations, then strategic, and then a few were deep. One reason why there might be fewer deep than in perhaps in other areas of mathematical practice is that the participants typically didn't know each other, so it's much harder to know who you're talking to and what sort of thing they might be asking exactly, and also because we've taken out all of the other areas of communication as well, so that impedes people from really knowing exactly what to say and what level to pitch it and so on. That's a possible explanation for that. Okay, so this is just a few examples of things that we found. So here's, this is a quote from the 2009 one. Is the explanation an answer to a why question? So this was flagged up because of this indicator here, because we answered yes, it is an answer to a why question, and then we identified what that why question was, although it was implicit. Why can we assume that it would be safe for the grasshopper to hop backwards to its previous point? In terms of the AI context that Walton talked about, the reasoning, strategic or deep, this was categorized as a trace explanation, so describing the reasoning at the object level, the reasoning trace, as it were. A strategic explanation, this example here, so we know that the correct solution will have to account for the fact that, and so on. This is talking about strategy, properties that the correct solution is going to have. And we did see some instances of the deep explanation. Here's another one. We saw one before. Here's another one. I don't understand Powell's proof. Can anyone elaborate the point a little further? And then here's the answer to that. And then he writes, thanks, now I get it, it's a beautiful proof. In terms of the breakdown of different types of objects in the mathematical context, 27%, sorry, the colours are not good colours at all, so if you, sorry about that. 27% were assertions, 19% were properties, 18 related to proof, so only 18 related to proof, 17 to examples, 8 to re-representation, and 6 to arguments, and then another 6 to the initial problem. In terms of the individual context that we looked at, 34% related to value, 32 to understanding, 20 to ability, and 15 to knowledge. And we also looked at how these things break down in terms of the explanandum and the explanans. So here, this is the personal context, so this is ability, knowledge, understanding, and value. And then the M's are the mathematical context, so initial problem, proof, assertion, example, argument, representation, and property. And the darker the colour red, the more instances we found. So, for example, a lot of questions about the proof were answered with the proof, as you might expect. So there was some symmetry in a way. If people asked for an explanation about an assertion or concerning an assertion, then the explanation itself concerned an assertion. So that's the diagonal line. But there's some darker spaces not in the diagonal which are interesting as well. So, for example, this assertion has been answered, or these have been answered with points about properties, and proofs here have been answered with examples, and so on. So I think this could be interesting for automated reasoning, automated theorem proving kind of communities, where if we can get a better grasp of what sort of explanation will be appropriate for different questions and what sort of mathematical object to raise, then if people ask questions, or I don't understand this bit, this thing, or this part of the proof, it might help to know what sort of answer that the system should give. So we'd like to continue this work. And okay, I'm going to speed up a bit so that there's time for questions. An example of persuasion, I don't believe this is possible, and then so there's kind of an initial conflict there. An example of information seeking, this was too simple, so there must be a mistake in my proof, what is it? And an example of pedagogy, here's a non-technical version of an early solution developed for use with a school group and so on. So that was a very unusually explicit one. But in terms of the social context, the dialogue split up like this. So a lot of it, 62% was inquiry. So we were expecting that to be a large number. We were actually a little bit surprised that it wasn't larger than that. 22% was pedagogical. Again, maybe not surprising given that it was sort of an educational setting. I mean, initially the problem came from that anyway. 9% was persuasion, where they disagreed and then tried to convince each other. 6% information seeking and not very much about deliberation. Again, you'd expect that because that's concerned with actions, but there were some that were categorised as what action should we take now, what should we do? And regarding whether they were given by the same person or not, in 76% of the case they were given by, sorry, that's the wrong way around. That should be in 76% of the case they were given by two different people, the explanandum and the explanandum, and 24 they were given by the same person. Yeah?
In the previous graphic, when you break down the types of communication, did you find examples of negative communication?
What do you mean by negative?
Insults.
No, not really. So we weren't looking for that, so I'm not saying that they're not there, because in our pilot inquiry, we found that they fit into the Douglas Walton's dialogue type. So after that, we purely categorised them in that, and if they didn't fit in them, they'd go in another category. But having said that, possibly because of the ground rules that people set up, possibly because people often were not anonymous, there were no insults. It was all very polite.
Oh.
Yeah. There was the functionality to vote for answers as well. So I think in a few instances they were voted down. I think people largely used that to vote up if it was good rather than down if it's bad. But I think a few were voted down a bit. Yeah. Right. So I'll come to the end here. So coming back to our 7 hypotheses, we've found support for almost all of them, just not the primarily appeal to higher level of generality. So again, bearing in mind the data set and the qualifications that we mentioned here, it's nice to be able to provide empirical support for some of the philosophical questions, or even to refute it, but to give empirical evidence for some of the philosophical questions that had come up. This categorization was extremely useful, and I think that's going to be relevant for AI. And then there are 3 hypotheses that we kind of invented ourselves were really borne out. So I'm glad that we did that. We found uncovered the assumptions that people make when they talk about explanation and challenged them and found evidence that those assumptions are not justified. So in terms of lessons for automated theorem proving or interactive theorem proving, explanations are an essential component of mathematical practice. It was concerned, well, in our data set, around 37% of them. And this is the backstage, the informal stuff. But explanations are used all the way through, not just at the end for a final proof, but all the way through for lots of different reasons, playing different roles at different times in the process, and concerning much more than just proof, concerning examples, assumptions, assertions, and all that. So I think in terms of theorem proving, especially interactive theorem proving, this sort of work will be relevant for enabling human users to develop a dialogue, I suppose, or a nice interaction with the system. So hopefully they'll be great to take up by human mathematicians. Okay, I'll stop there.
Great, thank you. Thank you. Is one allowed to say it's wonderful work on one's own paper? I'm not quite sure. Anyway, it's fantastic. I didn't really do very much of the work. Andy.
Can you go back to the list of hypotheses, the penultimate slide? So, well, no,
yeah,
great. So I'm really disappointed with the red cross on H3, because the area I work in, the primary means of explanation is an appeal to a higher level of generality. That's category theory. And I just sort of suggest that maybe it might be interesting to look at, there's probably a lot of unstructured, pretty unstructured, but a lot of data out there in various mailing lists, for example, where one can exactly see that the kind of explanation going on is somebody says, oh, why is this true? And another person say, well, that's just because it's a product in this category or something. So it's an appeal to a higher level.
So it's a really nice idea. I wrote earlier in the week as well that we should look at mailing lists as a nice source of data.
Unfortunately, they're very sort of unstructured compared to the.
I think our approach would apply to that, because if we search for the indicator terms, we can still do that and find a way of segregating maybe just one email or something for the random.
Actually, I think probably the best one to look at would be the NLab Wiki. Is that right? Is what's it called? I mean, the category theory mailing list wouldn't be a great one to look at because people are just talking about category theory. What you need is something where they're interested in, say, physics, topology, various subjects where category theory of a certain kind might be really useful, and then people will be coming in and saying, oh, well, this is true because I can see this is a category and blah, blah, blah.
Yeah. Thanks, that's a good suggestion. Yeah, we'll take that out. Yeah.
I would myself do this with the FOM mailing list. I think there are lots of explanations. I
think we might get instances
you get the heuristic
non-communication
there quite strongly.
If you don't know the FOM mailing list, it's, what can I say, it's a haven of charm, friendliness and welcome.
The insults, but I have a question.
We might need a few more dialogue types.
Did you do any cross-validation? So you categorized all those things, and I didn't. You went too fast. The difference between trace strategic and deep, I missed this. But I can imagine it's subjective.
It is a bit, yeah, it is.
So
I do take your point, it is a bit subjective. There were 3 people principally involved in this piece of work, myself, Ursula, and Andrew Aberdein. So we cross-validated amongst ourselves. There was a lot of discussion about it initially to get our categories, and then kind of ongoing discussion for specific cases.
So when it was unclear in specific instances, you did discuss, like, well, how should I put this?
Yeah. But still, there's an element of subjectivity, I think.
I mean, one can have a long discussion on methodology for doing this kind of thing, because the different methodologies in the HCI community, you do it differently, in the psychology community, you do it differently, but this was a fairly well-established methodology from certain parts of the social science field.
Sorry, the second.
Yeah, hello.
I have my poor mastery of English is the cause for this question. What does persuasion mean? Does it mean that you try to have somebody on your side without giving any explanation?
No, not necessarily. It just means that you start off in conflict, that there's some sort of disagreement about something, and each party is trying to persuade the other party of their point of view.
But using some arguments of authority or something?
Using anything. We didn't categorize it. So the thing that we, yeah, not force hopefully, but the thing. So we only came to this through explanations. So whenever we saw it, explanation was already involved at that point. But if we had done it the other way round and looked for examples of persuasion, then I'm sure we'd have found lots of other ways that they were using to persuade each other.
And the second question is about this hypothesis 7. How would you have decided that explanation is not a social phenomenon? What would have been the criterion to decide this?
Well, we formulated it as a we formulated it as a response to people not really mentioning that it's a social phenomenon. It seems obvious if there's an explanation, then there's an explainer and an explainee, but it's not obvious. People don't talk about it very much. So we left it very loose just to say that it's a social, and then in the pilot study fleshed out a little bit what we meant by that, which ended up being these dialogue types, which are obviously social interactions, and whether the explanans and explananda were given by the same person or not. Because our data set was a very social, it was a collaborative exercise, it would have been very surprising for that not to have been the case. But we might just have not found many explanations in the data set, I suppose.
Presumably, if one person gave all the explanation on the thing, that wouldn't have...
The example with the why, because we looked at why for the explicit why questions, and I said that we found 5. What I didn't say was they were all asked by the same person. So we did kind of at that point that we developed, our theory's got too specialised. It's explanation for one particular person.
Right, so Fred, you've had one question, and Arnold hasn't had any, so.
In the beginning you said you might want to say something about communication. Can you just give the title
oh, right.
of what would have been?
Sorry about that. Yeah, so I was keeping an eye on the clock, and I had loads more slides if we got to that. But I mean, this is going to be something to talk about offline for sure. But just to flick through and give you a tantalising sketch, that one, of how we're looking at informal mathematics and trying to derive ways in which we can describe that informal way, and also looking at patterns of patterns of communication. So Lakatosh is one that's very dear to our hearts, and so we've been looking for examples of the sort of reasoning that he described, which Ursula did mention. I think we do find it, it's reasonably common, I'd say. It certainly doesn't describe all of the communication, but it's not as productive as he made it in his Proofs and Reputations book. But we should talk more about it offline, I think.
Michael, yeah.
There's quite a lot of work on argumentation theory and argumentation annotations, and I would think that some of that really nicely applies here, especially if you go into one of the more confrontative settings where people really try to shoot down each other's arguments and so on, which is also a mode in math, of course. Have you ever tried that?
What we're doing, and by the way, Joe's very involved in this, so anyone who's interested can also talk to Joe.
Nick Joe's giving a talk next week,
it next week?
after.
Yeah, that picture might even show up again in my...
Yeah.
Okay, great. So principally we're using a thing called inference anchoring theory, which has been developed by Chris Reed and Kasia Budinska, which unites dialogue turns, so verbatim what people have said in a dialogue, with speech acts, so illocutionary aims, and then the argumentation form, the inferences that come from it. So it's a way of I suppose the phrase "whence inference" was the initial report that they wrote on this. Where does inference come from in a dialogue? And we're using that and extending that for mathematics.
I was more thinking of things like the attack or undercut or so
Yeah,
like
yeah, yeah, yeah.
that,
Yeah.
that are prevalent in argumentation theory.
Yeah, I mean, so okay, so that would be the left-hand part, the argumentation bit, where the inferences. Yeah, of course. Yeah, we have. I don't think I have any slides, but we have experimented with representing some of this work as an argument diagram. Sorry, with these attack and support relations, and premises, conclusions, and so on, as you say, and different argument schemes, and so on. All of that. Yeah.
Well, lots more questions and scope for discussion, but I think we're going to have to call a halt there so that the day stays on track. But thank you very much, Alison.